Yeah, sorry about that. So just to continue, it cancels out the noise that propagates on both the lines. So this to really deal with common mode noise. And another way, also suggested by the design guide, both of these are suggested, are Y capacitors. So they're these guys, and in the schematics, they are these capacitors. So how they work is that they essentially, any noise that propagates on this line and this line will be shunted to the same external ground. So the Vicor design guide suggests that we use like a chassis ground or a body ground of some sort that's not the same as our high voltage ground. It's a separate place for the noise to really be shunted and not reach back into either side of our power lines. We want to take it out of the system and to a different ground. So that's how Y capacitors kind of work. And those are the methods of common mode noise control in the DC-DC design. And then we get to our differential EMI filtration. And there is a lot of suggestions in the design guide. And the thing we went with is having this RLC filter that, well, basically on the input terminals, any differential noise, we could expect to be caused by any of the intense switching regulators or switching frequencies we expect in the surrounding systems. So for example, one thing we took into account when designing this EMI filter, by the way, this EMI filter, it's a low pass filter. It's when a certain frequency is being met, it will attenuate that signal, which means it will basically decrease it in such magnitude that it doesn't exist. And in that case, we are making sure only low frequency signals are going in, and any high frequency noise is being taken out of the system. So the way that this was designed specifically was using a filter tool powered by a Vicor module, which is pretty cool. And so in our slides, we can see that this is just the switching frequency expected from DC-DC, for example. And we can see that it could get as low as 400 kilohertz. So what we do to make sure that that's not affecting our DC-DC converter is that we have this simplified series damped filter. It's an RLC filter. And what this converter does, which is pretty cool, what Vicor does is it gives us, we can input our input requirements to our converter, and then we can check our filter, and then we can get our transfer function. And what it tells us is if we're meeting our attenuation goal, if it's optimally damped, if it's stable, and it kind of just tells you that you have a working filter. So that's this tool. I was playing around with values to make sure that it's stable, especially. It can get unstable if you vary the L1 and R2 too much, and that attenuates our target. So one thing, I guess, in design decisions that really went to this specific filter is that it was actually pointed out to me that the capacitors, when referenced to a pretty high voltage, they can be biased and actually have a capacitance that's much less than their rate, the product rating. And so I had to make sure that my filter wasn't dependent on that. So C1, like the way that this filter works specifically is C1, if I change it to 1 from a really small capacitance, it doesn't affect our filtration targets. So that was something else that I was really looking for in terms of designing a CMI filter. Cool. So that's how and there's a similar circuit, also an RLC filter on the output of our converter. And this is, once again, to make sure that we are not propagating more noise into the circuits after. And the difference being, this is now referenced to 12 volts, while this is referenced to 150 volts. Actually, yeah, let me make a point of that. So if you were not aware before, the DC-DC converter, its inputs is the battery pack, which has a nominal, I think, of like 130 volts and like, or 150 volts, and has yeah, so it's basically input to our converter, and our converter, we're outputting to 13.5 volts, which really equates to like 12 volts with line impedances, because it kind of drops throughout the connections. But it basically gives us our output voltage for our low voltage systems. So that's what the main function of this DC-DC is. It's literally powering all our low voltage systems. Okay, so we kind of talked about the EMI filtration and the differential EMI filtration, the common mode noise. So those are the main filter techniques on this board. And then we can talk about the bulk capacitance. So so these really huge caps you see on the board, they're bulk caps. And unlike decoupling capacitors or bypass capacitors, which I think are just a type of decoupling capacitors, they are not here to kind of like shunt high frequency noise to the ground. What they're here to do is to provide an energy source to the input terminals or to the output. Again, there's a bulk capacitor on the output and 2 on the input of 2,000 microfarads total here, 1,500 or 15,000 microfarads on the output, which are both extremely large. And as bulk capacitors kind of indicate in the name, they are large capacitors. So what they are energy storage devices. But when you have line impedances, or you have you base your module, your output of the bulk capacitors requires current, or requires more current than can be provided, and these bulk capacitors will provide that energy to the circuit, and so they will store charge, and they will try to maintain the voltage on their terminals by providing energy when necessary. So what the Vicor design or data sheet really says is that if you have line impedances that are varying, basically meaning if the input requirements maybe to the converter will change momentarily, or the impedances on the input before the bulk caps, we want to be able to have these bulk caps so that they can provide the energy source that's being temporarily altered by any sort of like resistances or reactances on the line. So that's what the essential function of the bulk caps are for, and that's why I added them. But you'll see shortly enough that I realized issues with them afterwards that required design changes. So before that, we can just really talk quickly about the Vicor module. Going back to our linearity of going through the system, you'll see that the Vicor module has all these pins, right? So the trim pin, its output voltage can be a certain number, or in a certain range, and that's determined by the trim of the this trim pin, which is when you have a certain resistor configuration, and there's actually a tool that Vicor provides to figure out what resistor config works for your trim and for our 13.5 volts. Then we have a fault pin. If the fault pin we have seen work, just because if it's going into like over current protection or over voltage protection, it will not output, and it will go and give us indication on the fault pin, which we are also trying to get that signal line to our power distribution just to know when DC-DC is faulting. You'll see that this is an opto-isolator. It's existent because there's 2 grounds that we have to reference when we're dealing with this DC-DC supply, or basically any DC-DC supply. It's because there's a high voltage ground and a low voltage ground. This is our signal ground. This is the ground. This is the reference we're using for all of our digital logic, all of our microcontrollers. And so there has to be an opto-isolator for the fault pin, which is referenced to high voltage ground to give us an output to our low voltage ground. So that's how that works. And our converter, just some stats about it itself, is it can output 240 watts at a current of 16 amps, and it can input 43 to 150 volts with a V out of 15 volts nominal if you don't put a trim or sorry, it's just 15 volts if you don't put a trim. If you do put a trim, it could be anywhere from 9 to 16.5 volts, which is, we put a trim for 13.5. So those are, so just some pins that the Vicor module provides and that we can use to our advantage, besides, of course, just the input and output pins you see on both sides. So now let's talk a little bit about the bulk capacitors and the inrush current. So the bulk capacitors, like I put them in, you know, the data sheet suggested them. They were, they're there for line impedances, but because they're bulk capacitance and because capacitors have, like when you provide power to capacitor, they essentially act as a short circuit. They will like draw a whole lot of current. Actually, we can see in the simulation, if I have, okay, so I have a simulation because I was trying to figure out what is the current I'm drawing during inrush and how can I make sure that it's not damaging, or how can I prevent it from damaging the rest of the circuit, or especially the contactors. You can see in this diagram that the inrush current will kind of, like, if it's high enough, it can cause an arc between the contactors, and that can possibly, if it's really like it has a high enough magnitude, can weld them, and that's not good because then we're basically we can't control our relays anymore. Not good. And so I had to come up with a few solutions, but just to kind of like understand what kind of inrush current these bulk capacitors are really providing, we can look at the simulation. So if I run it and I look at the current, I guess here, we can see that at the very beginning, it's reaching like 2.4 kiloamps, which is crazy. For very momentary time, but that's not good. We do not want that much current. Also, this is a simulation, so it doesn't include the impedances, and so it wouldn't be really that high, but just to get the gist, it's like pretty crazy. And so the simplest solution was to add ICLs, which are inrush current limiters, in series with the input. And so the way ICLs work are they're essentially resistors, but they when they're cold, they provide a resistance that's much greater than when they're warmed up, and they warm up to a significant extent when they have current going through them. So that's why I kind of want to save this for later, because this circuit was implemented after I realized the inrush current problem. And so you get these two ICLs, and I kind of did the calculations for each of them for what they would heat up to and what kind of voltage, or what's it called, resistance I would be expecting when they're heated up. And the important thing about ICLs is that when you're getting the inrush current, you're blocking, you're limiting the current because of the resistance of both resistors. But when they are warmed up, you don't want it to be, you don't want to have inefficiency by making these making voltage drop across these resistors such that it actually affects your DC-DC converter. You're not getting your full input. So that's how they work, and that's why they were added. But another thing that these bulk capacitors do is that they hold, so once the relay is open and DC-DC is isolated, from testing, actually, Micah found out that, like, which is expected, that the time that the capacitors take to discharge is like 15.5 seconds. But we have to remember that these bulk capacitors, they're like referenced at like 150 volts. So having 150 volts present in your system after a switch has been opened to isolate the system is not good, especially for 15.6 seconds. It's also against WSC regulations. So the solution to that was to add a discharge circuit. And here we go. Here is the discharge circuit. I'll just quickly explain it. I know I've been taking a really long time with this meeting, but the way it works is that there is a Zener diode here, and its drop is like 68 volts. It clamps 68 volts at its cathode. So when we have our voltage at 150 volts or whatever, and it's great enough, there's current that's going through here, and it's turning on this NPN, which is essentially shunting the current to ground. Sorry, I just edited my circuit. Let me fix it. Shunting the current to ground and not turning on this FET. So this resistor dropping, the way we discharge this capacitor is by making the energy from this capacitor just drop across our resistor here. And so when the voltage is high enough, it won't drop anything. But once we open the circuit, the voltage is rapidly dropping, right, from the input here. And so once it reaches below 68 volts, this guy will stop conducting, this NPN won't be on. And what we do is we have a shunt regulator here, which we talked about before, what shunt regulators are. And what its essential purpose is to provide the energy to our capacitor here to also be an energy source to turn on our FET over here. And what we get is that this FET is on, there's the energy from the capacitor is being dropped across the resistor, and our circuit is much better. So if I run it now, we see that, okay, one sec. We see that the voltage on the capacitor, it actually gets to like 5 seconds, or it gets to under 30 volts at like 3 seconds, which is much better than 15 seconds. And if we don't have our discharge circuit, it actually takes way longer to get to 30 volts. So we can see how this kind of works and how the output is kind of what we want. And so that's why it was implemented. And so, yeah, the safety mechanisms for our inner current are our ICLs, our fuse, and well, the discharge circuit is really looking at once the relay is opened, that we aren't holding a high voltage for way too long. And so that was a really long session. I'm sorry about that. But any questions at this point, or anything I missed in the chat? Anything at all?
Nothing's in the chat, if that's what you're wondering.
Any questions about the converter itself? What is this? What is that? Also, this LED is just to indicate that there is power on this output, that we're getting 13.5 volts.
Do you want to explain the second output connector there?
This guy?
The microfit.
Oh, yeah. So we actually, yeah, that's a good point. Another thing about this converter is that it generates a lot of heat. Although DC-DC converters are efficient, and this is way more efficient than if this is a linear regulator, it still generates a lot of heat. It's like 90% efficient. And so 10% of like the power is actually being dropped as heat. So it heats up, and what we need is a fan control. And so that we have an accurate fan control, what we're doing is that this connector is giving it, we're getting this, this goes to power distribution, by the way. We're getting a 3 volt reference from power distribution, and we're going to drop that across the resistor divider with the thermistor that will be attached to the heat sink on our DC-DC converter. And then we're getting temperature feedback that's going to power distribution that'll control a fan that will cool off DC-DC because it gets really hot, and that's not good. And again, one of the pins is for the fault detection from our converter. Any other questions? That was a good point. Also, these headers, Josh talked about it a bit before, but they have to be rated for pretty high voltages, like the barrier does, and this guy has to be rated for pretty high currents. So those are just design decisions you have to take into consideration when you're choosing connectors.
I have a question about the P1 connectors. It says it connects to chassis body ground right below the
Here?
converter there. Yeah.
Yeah.
So how does that work?
So Okay, if we find that our common mode noise is not being dealt with enough by our choke here, what this does is I just put a pad here that we could like literally solder a wire to any chassis ground. A chassis ground is like a large body ground. Technically, we could use the actual chassis of the car. And the only issue with that, of course, is kind of safety. I mean, like if this was to like somehow fault, or like short somehow, or something went wrong, we don't want to take out the entire like mech team that's used touching the chassis, but we essentially want to use like a separate isolated ground that's a different reference. And I have a pad here because I just put something in so that we could just solder a wire if we wanted to. So until we use this ground, these Y caps don't do anything. Good question. Anything else?
Where is a signal ground physically located?
Sorry, this to the ground?
Yep.
Yeah, so this ground is like the ground that's carried out through the entire low voltage system. If you ever draw a ground on your schematics, it's going to be tied to this ground for any like digital communication. It's like completely like when we connect DC-DC on Power Select, this module is basically giving us our reference to ground because it's our power source at this point. It's isolating our high voltage ground, but it's providing the reference for the ground that's literally carried out through the entirety of our low voltage systems. Does that kind of make sense?
Yeah, it makes sense.
Okay, cool. That was also a good question. Oh, another thing you might notice is why are there two caps here? Well, DC-DC is a really long board, and something to help in case somehow a capacitor is removed from its pads. We don't want that to happen. Like if that happens, we have another capacitor that will like literally be positioned horizontally instead of vertically, so that if stress on the board somehow breaks C8, C7 is still there, and we don't have to worry. Any other questions?
I guess to follow up on that, why did you
Mhm.
choose to use series capacitors as opposed to parallel ones?
Right. So the thing is that if somehow we like broke this or it stressed and it like if like let's just like take for example, this wouldn't happen to the bulk capacitor because they're big, but and if it somehow like broke or like shorted, we're basically shorting our entire like positive to our negative, and that's not good. Something will like really get hot, or the capacitor will. But if we have two in series, what happens is if this guy breaks, this guy is still here. So there isn't a shunt to ground. Does that make sense?
Yeah, that makes sense.
And they're placed at 9 degrees to each other so that if the board's flexing in one direction
Yeah,
and
exactly.
it breaks, if it shorts one together because it flexes, say, along the length of the board, then that's not also going to break the second one.
Yeah. These are good questions. Any others?
I guess another question. Not sure if you mentioned this before, but for the DC-DC converter module,
Yep.
is this a switching regulator topology, or is it like?
Yeah, it's exactly that. It's a DC-DC buck converter.
Oh, I see.
Yeah. So inside you will see something extent of this guy, definitely more refined, and it has its own, of course, control loop because our specific module, it's able to take in a variety of input ranges and it's able to provide a variety of output ranges. So plus it has all this trim enable and volt pin. So there is a lot. It is a thick module. It is pretty big, but its topology is of a buck converter. This is the guy. Yeah, I actually linked the design guide if anyone is curious on one of these slides. It's pretty cool to look through it. Yeah, it's very intense and very well laid out. So anyone can make a converter. And the datasheet. Cool. Well, I'll give another minute for any questions, but otherwise, sorry. I think my meetings are just really long, or my knowledge shares. I think I just ramble, but it's okay.